For our next example on finding centers of mass, I want to consider a system which is a bit more complicated. In our last example, we considered a system that occupied 2 dimensions, but it consisted of 3-point masses, m1, m2, and m3. This time, I'd like to consider a problem which is a little more ambitious. Let us consider, instead of a small finite collection of masses, let us consider a plate of uniform thickness and density. And for purposes of simplicity, we'll suppose that this plate is bounded below on the x-axis, bounded on the left and the right by x equals a and x equals b, and bounded above by the curve of some function y equals f of x. So you can imagine a plate of some uniform thickness and density that has this shape. And our question is the same. What is the center of mass, or where should we position a special point about which, if the whole system is turned in space, the plate will balance perfectly? Over here, down here. That's our question. So to do this, let us first consider this simpler question. I'm going to choose or select out of this plate a thin vertical strip which has length, you may have guessed, delta x, and ask what the center of mass of just this plate is. So what's the center of mass of this plate? Well, if the plate is of uniform thickness and density, then we can make one really important simplifying assumption. We can assume that all of the mass in the plate is centered right at the center of the plate, or of this particular rectangular strip. Now that's a really useful simplification. So let's calculate the coordinates of this point in the center of the vertical strip. The bottom coordinate of the strip has coordinate x0, and the top coordinate of the strip has coordinate x comma f of x. So what are the coordinates of this point right here? Well, its x-coordinate is just x. Its y-coordinate is the one that's in between this y-coordinate and this y-coordinate. How do you get the y-coordinate that's right in between? Well, that's just the average of the 2 y-coordinates. So to get that one, you take the 2 y-coordinates, in this case 0 and f of x, and divide by 2. Or you get x comma f of x divided by 2. Great. So those are the coordinates of the center of this plate. And again, we can assume that all of the mass and that this whole vertical strip is concentrated right here at this point. This turns out to be really convenient for the purpose of calculating moments. So let's take this one particular plate or point and calculate first its x moment. Now remember the switcheroo, the x moment is found by taking the y coordinate and multiplying it by the mass. So the y coordinate is f of x divided by 2, and then I need to multiply that times the mass. Well, I haven't told you what that is, have I? Well, I need to tell you this. I told you that the plate is of uniform density and thickness. So let's denote by delta the density of the plate. So now how do you get the mass of the plate? Well, to get the mass of the plate, you need the density, and you multiply that times the area of the plate. So we have y coordinate times mass, and mass is density times area. And, well, here's again the y coordinate. The density, the area of this plate is just the width times the height. The width, as we know, is delta x, and the height is just the value of the function up here, this y coordinate, f of x. So the total moment of this vertical strip, the x moment, is, if I rearrange these terms a little bit, I get what? Delta over 2 times f of x squared times delta x. That's the x moment. What about the y moment? Well, the y moment is the x coordinate times the mass. And the x coordinate of this plate is just x. So here we get x, and the mass we already went through the trouble of calculating. It's the same expression as this right here. It's density times area. So here we get x, rearranging just a little bit. Delta times x times f of x times delta x. That's the y moment. Now, of course, to obtain the x center of mass, we take the sum of all moments that is the sum of all y moments, and we divide by the total mass. We have the y moment, for example, for this one strip, and to get the sum of all y moments, all we need to do is integrate this expression. But we still need the total mass. What's the total mass of the system? Well, the total mass of the system is the sum of all of the masses of the vertical strips. The mass of this one strip that we had featured above, this one right here, is again the density times the area, and that is density times height times width, right? That's just the mass of the one strip. And so to get the total mass, we sum the masses of all such strips and take the limit as n approaches infinity, and that gives us an integral delta f of x dx as x ranges from a to b. So that's our total mass, and we denote that by m for total mass. So now let's put it together. We have this formula for x bar, the x center of mass. That's the sum of all y moments divided by the total mass. X bar equals sum of all y moments divided by the total mass. Sum of all y moments can be obtained by integrating our expression for y moment given above. And the total mass can be found, well, which was given directly above, integral from a to b delta f of x dx. I did make one small error. I'm integrating. This is not a delta x, but a dx. So this gives us our total, our x coordinate for center of mass. Of course, the y coordinate for center of mass can be found in an analogous fashion. The only difference here is that the y coordinate for the center of mass is found by dividing the x moment by the total mass. Now the x moment is another integral, but it's the integral that we found up here. This one right here. So for this x moment we integrate delta over 2 f of x squared dx over total mass, which is the same expression as this one right here. And we have expressions for both the x and y coordinates of the center of mass. Now, one thing you might notice about these formulas for the x and y coordinates of the center of mass is that they are each fractions. So let's look at the x coordinate here for the center of mass. It's this integral over this integral down here. You do have constants which occur in each of those integrals, in particular these deltas right here. These deltas can be factored out of the integral, and when they do, you might notice that they immediately cancel out. So the moral of that story, and the same thing happens for the y center of mass down here. You get a 1/2 after you factor this out, and then these deltas cancel out with one another. So what that means is that the density of the plate should not or does not have any effect on where the x and y coordinates of the center of mass are. And that should make sense, as long as we abide by our requirement that the plate is of uniform density and thickness. The density should not affect where the center of mass is located. It'll be the same whether the plate is constructed out of a uniform piece of wood or tin or iron or whatever substance you have. So here are our formulas. Let's do an example. The example I'd like to do is the following. What do you think the center of mass is for a plate which is shaped like the region under the parabola y equals x squared as x ranges from 0 to 1? So if for whatever reason you build a plate that is shaped like this region under the parabola, and you want to suspend that plate horizontally and balance it on the head of a pin located somewhere inside of this region, where would that head of the pin be located so that it doesn't torque off or unbalance about that point at all? That's what we'll calculate. So this center of mass, again, is denoted x bar comma y bar. We have the expressions above to obtain it. So here we go. First of all, I would suggest that you begin by calculating the total mass of the system. And remember, the total mass of the system is integral, well, in this case, from 0 to 1 of f of x dx, and that's just the integral from 0 to 1 of x squared. Then you integrate that, and you get 1/3 at the end. So the mass is 1/3. Now notice if you're keeping careful track of things, I left something out of here. I left the density out of it. What happened to the density? Well, fine, I'll throw it in. Density, density, density. So the mass is really 1/3 times the density, whatever the density is. But remember, at the end of the day, the density is going to cancel out and will not affect our answer. So I hope you don't mind if I just don't include it here, because ultimately we won't need it. So there's the total mass. Now let's calculate the y moment, m sub y. Remember, that's equal to the integral of x times f of x dx. And so in that case, what do we get? Integral from 0 to 1 of x cubed. And if you find the antiderivative, evaluate it at the endpoints, you just get 1/4. Now let's go on and calculate the x moment, m sub x. Well, that is the integral from 0 to 1. There's a factor of 1/2 in there because of the geometry of the strips that we used to approximate the region. 1/2 f of x quantity squared dx. And that is, you can factor the 1/2 out, 1/2 integral from 0 to 1 of x squared squared, or x to the 4th dx. And for that, you get 1/10 after that calculation is all said and done. Now we're ready to write down our center of mass, x bar comma y bar. X bar is m sub y over m. Y bar is m sub x over m. And so we get what? My over m is 3/4. Mx over m is 3/10. So there's our center of mass, 3/4 comma 3/10. And if you go back up here to our parabola, my drawing's any good, 3/4 is somewhere, well, that's pretty good. 1/2 is somewhere right about here, so 3/4 is somewhere right here. So there's our x bar. And 3/10, that's about 1/3. If this is 1, my drawing's not that bad. 3/10 is somewhere in here. So that's a pretty good guess for our center of mass if I had to eyeball it. 3/4 and 3/10. So hopefully this example shows you how you might handle such a problem for a more complicated center of mass. For example, I won't compute or calculate the whole answer right here, but another question one might encounter, which is common, is what is the center of mass for a semicircular plate of uniform density? And my drawing's pretty lousy, but pretend that the semicircular plate is positioned symmetrically with respect to the y-axis, so it's perfectly centered about the y-axis. And for concreteness, you could say maybe this plate has radius 2, for example. So what's the center of mass? If you had a plate made out of a semicircle, where would you balance the plate? Well, one of these coordinates is really easy and you don't need any calculus. If the plate is indeed situated symmetrically with respect to the y-axis, then the x center of mass is going to be right here in the middle somewhere, or x bar equals 0. So you know that's going to equal 0. So don't do any calculus for that part. The only calculation you need to do here is for the y center of mass, or y bar. And again, that'll be m sub x over m, right? So that'll hover somewhere between, well, 0 and 2, right? It would be naive to expect that the center of mass is smack dab in the middle at y equals 1.